So I want to talk about today, for the most part, individual fairness, which Cynthia set up for us in the morning. And kind of explore issues that Cynthia was hinting at about how we do machine learning that's individually fair, how we do automated classification, where does the metric come from. So those are all really exciting and interesting questions. And I have more questions than answers. I think that probably applies for the entire course we're teaching. So there is some stuff that we understand. There is much that we don't understand. And I think it's a really exciting time and a really exciting area to be doing research in. So that's an invitation to all of you. Okay, so individual fairness. So the assumption is that we have a metric that tells us the distance between any two individuals. There we go. So throughout my talk today, we have some feature space, big X. That's where individuals are coming from. And for any two individuals, the metric gives us the distance between 0 and 1. And we'll use these properties. I'll get back to them later when I talk. But what is a metric? Well, a metric is a distance function that satisfies symmetry, the triangle inequality, and this property, forget what it's called, basically saying that if the distance between two individuals is 0, that means they are identical. Okay, they have the same features. Do you remember the name of the property offhand? I have it somewhere in my notes. We'll get back to it. Indiscernibility. Indiscernibility. Okay, so we have our metric. Individual fairness tells us that similar individuals should be treated similarly. So we have some allocation or some outcome computing function, which is going to map our individuals to some outcome space, or rather to distributions over an outcome space Y. And I'm just recalling stuff that we've seen. We'll say that this outcome function is individually fair if for every two individuals, x and x prime, the distance between their allocations. And for my talk today, we're going to think about L1, or statistical distance. Okay, so let's put the differential privacy distance aside for right now. And really, we're talking about statistical distance, or L1. So the difference between their allocations, and remember again, it's a probabilistic allocation, so these are two distributions. And the distance between the two distributions is bounded by the distance according to the metric. So this gives us the formalization of similar individuals should be treated similarly. We'll see later today, I want to talk about this as perfect. Either perfect individual fairness or perfect metric fairness. So good, that's our fairness requirement or inspiration for today. And now I want to take a detour into learning, machine learning, or classification, so we can talk about fair machine learning. Okay? So,
silly question. So
yeah.
The only way that this metric enters is in constraint on what kind of function C you have, right?
Right, it's constraining the types of outcomes you can assign or the types of allocations you're giving.
So in other words, you might as well just start with some class of functions that you consider Lipschitz, whatever that is. You don't have to have for that class to come from an actual metric and be Lipschitz for that metric. You could just specify a set of functions that you believe to be Lipschitz.
So the question is Lipschitz in what? Because the metric could simply say, I'm not sure I totally understand the question.
I give you a space of functions and I say these are the functions which I call Lipschitz. They're not Lipschitz for anything. I just call them nice functions.
Right. So I think the important thing, and I don't know if this is getting at your question or not, but the metric might say that everyone is different, right? And then there's no constraint. We can just do whatever allocation we want. Okay, so it's not that there is necessarily always a Lipschitz constraint. between any two individuals. If the distance between the individuals according to the metric is 1, as far as I'm concerned, they're totally different, and we have no constraint. So it's really important, I think, to have this metric front and center to tell us what our fairness constraints are. Did that answer your question? Good. Other questions? Okay, so I want to talk about machine learning today, so let me erase this. So for that, I still want to assume we have our same feature space of individuals. So every individual is in some set X. Those are the features. As Cynthia said in her talk, the features can be super important, but let's assume that they are fixed. So we have our feature universe X, and we have a distribution D, which is unknown to us, okay, over labeled examples. So individuals and a labeled. And the label is going to be 0 or 1. Okay, so you can think about the label as, did this student do well in college? Did this patient develop a disease? Did this treatment help the patient? Okay, so we have our Boolean labels. We don't know the underlying distribution D, but we see samples from it. Okay? So really what we want in the end, or the goal when we're talking about supervised learning, we want to learn a function, which we'll call the hypothesis, that lets us predict what the outcome of individuals will be. Okay, so in comes a new individual, and we can predict and we try to predict what their label will be. And ideally, we want, it's easy to produce just something that labels everyone as 0 or everyone as 1, but we want to have low error. So usually our goal is to minimize some error, where the error of this hypothesis H, there are many different error functions we could use, but here in binary classification, there's one that makes particular sense, which is just the probability over this underlying distribution that we label an individual or an example incorrectly. Okay, so our goal is to produce hypothesis with low error. The key issue, notice, is we want the error to be small with respect to the underlying distribution of examples, the distribution of patients, and do they really develop a disease, the distribution of students, and do they really do well in college. So the key challenge when we're talking about machine learning is we don't know this underlying distribution. We just see samples from it, and then we try to train some hypothesis, and we hope that the hypothesis generalizes, meaning that its error is good or its error is small, not just with respect to examples we've seen before, but also with respect to unseen examples. Okay, so that's the key challenge, and the learning algorithm, so that's our goal. When we talk about supervised learning and we talk about what we call the batch setting, the way we try to train this hypothesis is we just get a bunch of labeled examples. So the learner gets a training set, okay, xi and yi, that we assume are drawn IID from the distribution D. Questions? Have people seen this? I mean, are people familiar with pack learning? I see some no's, I see some yeses. I know you're familiar. Okay, so when I say that we're trying to minimize the error, what's a good error? If we get 90%, is that good? If we get 80%, is it good? It's unclear, it depends on how challenging the classification task we're talking about is, right? If we're trying to identify numbers in the MNIST data set, maybe we want accuracy that's close to 100%. For other tasks, if we're really trying to predict whether an applicant will return a loan or if a tumor will metastasize, maybe 90% is just unachievable, and we have to settle for lower errors. And the the answer is really task dependent. So the approach in agnostic learning or in agnostic pack learning is we don't try to achieve some absolute number like 20% error necessarily. We try to compare with a benchmark class of hypotheses. Okay, so we compare to some benchmark class H. And we try to do as well as the best hypothesis in H. So maybe H is all the decision trees. Maybe it's all the neural nets of a certain architecture and depth and size. Maybe it's, hyperplanes or something like that. But we have some benchmark in mind. And the goal is to approach the error, is to produce something that is as good as anything in the benchmark class. Okay, so the error of the class H is just the minimal error of any hypothesis in H, and we're going to try to do better than that, or nearly as well as that. Okay? So that leads us to the definition of pack learning, which will be, so all of this is a detour through learning and binary classification. Once we have a little bit of background of what we have in mind, then we'll turn to thinking about fairness. Okay, so we're trying not just to learn how to classify people, but we really have some underlying metric or some fairness constraint in mind. How do we think about that? So first, without fairness, pack learning, due to Valiant, this, okay, hopefully it doesn't tip over. So a learning algorithm, it's a requirement from a learning algorithm, and in a nutshell, thank you. The requirement is that no matter what the unknown distribution is, if the learning algorithm gets a sufficient number of labeled examples from it, it can produce a hypothesis that is competitive in terms of its error with the benchmark class H. Okay? So we say that a learning algorithm L is a pack, and it stands for probably approximately correct learning algorithm for a class H. If for every distribution D, whatever the distribution on labeled examples might be, and for every error parameters that we might want to achieve, epsilon and delta, epsilon is how close we come to the error of the best hypothesis in the class H. Delta is sort of a global failure probability, the probability that we simply fail to generalize, to produce a good hypothesis. There exists sample complexity, a number of samples. Usually we want it to be polynomial in 1 over epsilon and log of 1 over delta, but let's not get into that. Such that when we run the algorithm, so we run the algorithm, the learning algorithm L, on m labeled examples, okay, x1, y1, up to xm, ym. The probability that the error of H is too large on the underlying distribution, and by too large I mean it's epsilon, more than epsilon larger than the best hypothesis in our sort of benchmark class H, this probability is small. Okay, and the probability is taken over the samples which we draw from the underlying distribution and any coins tossed by the algorithm in L. Okay, so that's kind of a very nice agnostic pack learning, a very nice kind of guarantee for a learning algorithm when you can get it. Okay, and the probably approximately correct probably is the failure probability delta. That's essentially the probability that we fail to generalize. We produce hypothesis H, which might be really good on the training data, but isn't good on the underlying distribution. And approximately is up to this slack epsilon. And both of these are essential if you want to do learning from a sample. Okay, and I kind of want to say two words, doesn't have directly to do with fairness, but two words about PAC learning. So one key question in PAC learning is computational complexity. So is the learning algorithm efficient? Does it run in polynomial time? And that can be really hard, even for simple classes, even simple benchmark classes. It can be hard to get agnostic PAC learning algorithms, and we'll come back to that. And this kind of the tension today when you think about, especially from a theoretical perspective, when you think about machine learning, is that in practice we have these algorithms that are doing really, really well. In theory, we know things are hard, and I think, fairness aside, these are excellent questions to be thinking about, sort of what's going on there. And we'll talk about, I want to mention the computational complexity of PAC learning because it's going to come into the computational complexity of fair machine learning, which we'll talk about later, later in the course. So either everything is clear or nothing is clear. So it would be nice if someone asked a question to disambiguate. Okay, so good. So this is kind of a great definition that we would think of when we're just thinking about accuracy for machine learning. But of course, we're here not just to think about accuracy, but also about fairness. Okay, so how would things change? If we wanted to also think about fairness, well, maybe H is a very accurate classifier on your training data, but as Cynthia very clearly and persuasively argued, there could be a lot that's already biased in your training data. The fact that H is accurate doesn't mean at all that it isn't discriminatory. Okay? So, and that's, when we say, is H fair, there are lots of questions. There are lots of things that could mean. Is it discriminatory? So luckily, we now have this vocabulary for talking about fairness, which is using individual fairness and using the metric. Okay? So basically the question is, are individuals who are similar according to the metric being given similar classifications? And if they are, then I could say this is, an individually fair or metric fair classifier. Okay. So notice here, and this is really important, thinking as computer scientists, we said that when we talk about fairness, we want our classifier, whatever's producing the outcomes, to be probabilistic so that we can compare the distributions over outcomes of individuals. So when we talk about fair machine learning, we're going to talk about a probabilistic classifier. H, okay, so it's taking an individual and giving them a distribution over the outcomes 0 and 1. And now individual fairness for the classifier would mean that for every two individuals, x and x prime, the distance between the distributions of their classifications so again, here I mean L1 or statistical distance is bounded by their distance according to the metric. Okay? So this is what I want, and if a classifier satisfies this requirement, we're going to say that it's individually fair. And all of our context about, who are the groups, what kinds of fairness concerns do we have, what's the task at hand, who are similar or dissimilar, those all come to us through this metric, D, as they did before. Okay. Yep, go ahead.
So h of x, is that a real number between 0 and 1?
You can think of it as a real number between 0 and 1 because we're talking about just two possible outcomes. So it could just be the probability of outcome 1 and the probability of outcome 0, but I encourage you for now to think of it as a distribution.
Okay, so then how are you defining the L1 distance?
Okay, so the L1 distance between two probability distributions is the sum over all possible outcomes of the probability assigned by the first distribution, the absolute difference between the probability assigned by the first and second distribution. So that's kind of L1, or statistical distance between two distributions. If the distance is small, it sort of bounds the advantage that any distinguisher can have in distinguishing the two distributions. That's just a standard measure of distance between, maybe the standard measure of distance between probability distributions.
Just out of curiosity, have people looked at different distance between the distributions for this?
At different distance measures between distributions? Yeah, so Cynthia talked about the differential privacy, or L infinity distance, where we look at sort of the maximum, the ratio between the maximal ratio of probabilities, kind of the difference for the worst case possible outcome. So that's one. People, I think, do think about things like Hale divergence between distributions, but really I think this is kind of the canonical measure. Okay, so great. So that's our goal in terms of getting to a fair classifier. I just want to make the distinction today, and I think in the early part of tomorrow, we're going to talk about individual fairness, and we have a metric, and that defines fairness for us. And then we're going to shift to talking about, different notions of fairness where we don't have a metric. For today, we have a metric. The metric is our friend. That's what's defining fairness for us. So question, we have our fairness constraint. We have our distribution on labeled examples. Perhaps we have a benchmark class H. Can we learn, it's very natural, can we learn an individually fair classifier? So any thoughts? Like a serious difficulty here?
Do you have to restrict the hypothesis class to like a set of individually fair hypotheses?
Could you repeat, sorry?
Do you have to restrict the hypothesis class to the set of individually fair hypotheses, because otherwise, like H star is not necessarily individually fair?
Yeah, that's a great question. So you're 2 steps ahead of me, but I think the comment was that if we're going to talk about accuracy along the lines of PAC learning, if we're trying to compare ourselves to the best hypothesis in H, that might be a losing game, because the best hypothesis in H might not be fair. So it's not a fair comparison. It's not a good comparison, right? So that's one difficulty that we're going to have. But as I think you already suggested, we can get around that by sort of reimagining our benchmark and saying we want to do as well as the best fair hypothesis in H. And that is what we're going to do. Another difficulty? So serious difficulty is this. Okay, in particular, the for all sign. Okay, so I get a set of labeled examples for my training set. And maybe I learn something that's fair on those M examples. Okay, so I see no violations of the metric fairness constraint. But in individual fairness, and Cynthia was making this point as well, the requirement is much stronger. It's not just for X and X prime that we've seen in our training set. It's for every X and X prime in the world. And how do I know now? Here is my classifier. I don't know what the underlying distribution is. I don't know who the X and X prime that I need to worry about are. How do I know that my classifier is really individually fair, that it's fair for every possible person in the universe that I haven't seen yet? Maybe there's this really esoteric subclass, one person in the whole universe who I've never seen, who looks different from all other people, and for them the hypothesis isn't fair. I don't know. And this is a fundamental difficulty. If we really want, the strong or perfect fairness constraint for every X and X prime, generalization is a huge difficulty, and we're just not going to be able to do it. Okay, so we need to relax this for all. Good. So that leads me, I want to leave that right there, to the definition of approximate.
Sorry, but something I don't understand. So this metric is over X, right? It's not over the outcomes.
Yep.
So therefore, in principle, you have access to the whole space a priori, right? So you could just maximize or minimize whatever over Lipschitz functions, and in principle, so like in the learning situation, your problem is that you don't have access to data that's hidden from you, right? That's why you cannot in principle fit the correct distribution, whereas here that problem is not there, right? I mean, you can optimize within Lipschitz functions. And
Yeah, very good. So I tried to cheat and I didn't get away with it, but it's a good, you're making a very good point that I should have, we should dwell on. So thank you for the question. So there's no fundamental difficulty with producing something that is perfectly individually fair, right? I could just give the classification 0 to everyone, for example, right? Everyone gets exactly the same distribution. The distance between, the classification of every x and x prime is 0. Individual fairness is satisfied. So it's possible, and it's possible to do even better. I could pick whatever classifier I want and now enumerate. X is a finite set, it's big, maybe it's exponential, but I could enumerate over all x and x prime that could potentially be out there and verify that this inequality holds. So there are two difficulties. One difficulty is computational, right? I don't want to just classify everyone as 0, we want to be accurate, right? We're not giving up on machine learning, we just want to make it fair. So one difficulty is computational, and if we have time at the end, maybe I'll say a word about that, but I wasn't planning to. And the other difficulty is not computational, but it's related to performance. So, suppose we do enumerate over all the pairs of people that could be in the world, and we find some collection of attributes such that if it appears in the world, then the classifier will be unfair. We have no idea whether this is a real problem or we've just imagined it. So we could be wildly too conservative in particular, there's no hope, as someone was saying here, of approaching the performance of the best fair classifier, right? Because the best fair classifier is measured with respect to this underlying distribution and doesn't need to worry about all possible potential sets of people.
So your point is that this distribution you're trying to learn could actually be simply identically 0 in a large part of X.
Yeah, it could be the support. I imagine that the support is a subset of X. It's not everyone, not all the possible collections of features. Yeah. So those are the two issues that we want to overcome. One is computational. The other one is sort of information theoretic. Who are the individuals that we really do need to worry about that really are in the distribution? Okay.
Wait, sorry, can you repeat that last point? So if D has zero mass on some part of the support, but do we still need to be fair with respect?
No. So if there are no people who are into juggling and kittens, if that intersection of people does not exist, then I don't care if my classifier is unfair to people who like juggling and kittens.
So for all should really be almost surely, and then you see the dependence of the distribution.
Good. So really what I want is what we call approximate metric fairness. And the reason I'm moving, I don't want Cynthia to get upset, so I'll say the reason I'm calling it metric fairness and not individual fairness is that now we are going to be giving up on some individuals. Okay, we're just going to require that this condition holds with very high probability over pairs of individuals drawn from the underlying distribution. But we could call it approximate individual fairness too. I'm not super attached. Okay, so what do I want? I say that H, then my classifier H is alpha gamma approximately fair if the probability over x and x prime drawn from the underlying distribution that the fairness constraint is violated if this probability is at most alpha. So with all but a small alpha probability over pairs of individuals, the metric fairness constraint is satisfied. We also allow in the approximation an additive gamma here. You might not think we have to have it, and you would be right, we don't have to have it, but it turns out to be really useful for building algorithms. We want to build algorithms, so we allow some slack in terms of a minimal deviation from the fairness guarantee, additive deviation from the fairness guarantee. And with this notion in fairness in mind, we will be able to build fair learning algorithms that generalize beyond a sample and achieve competitive accuracy. Okay, so that's the goal in defining this relaxation. Now, it's up for debate. I'm not in, personally, so this is due to work with Gal Yona. I'm not in love with the fact that there are individuals where the classifier will simply fail to be fair. Okay, so all the definitions we give you during the course are up for debate. Nothing is ever canonized in science, but certainly in this field, things are not canonized yet. So the advantage of this definition is that it does allow us to generalize beyond a sample, and it's essential to have such a relaxation if you want to generalize. But I don't want to take lightly the fact that there are pairs of individuals, or there are certain individuals where they might be treated unfairly. So that has to be front and center. There is some guarantee, since we bound the probability that it happens. If you think, for example, about a protected set, if their mass is much larger than alpha, then usually they won't experience fairness violations. So there is some guarantee here also in aggregate for protected sets if you worry about them and if they're large enough. Try a different mask permutation. Good questions about this? Okay, so I want to say that we have made major progress. And in particular, and I think we'll come back to this throughout the course, this question of auditing a classifier or a risk score, auditing them for fairness. Meaning, can we actually tell, given some data or given the classifier, is it fair or not? So I want to say that here already we can audit for fairness. And that's major progress. Okay, so we can audit using a sample of data. Okay, so I want to say that if H is alpha gamma fair on a sample of IID labeled examples drawn from D, then it will also be almost as fair, alpha prime gamma fair on the underlying distribution. Okay, so what's the technical claim that I want to make? For any classifier that you give me, and for any epsilon and delta that we may want, error parameters, the probability that the hypothesis is sort of fair on m samples drawn from the underlying distribution, but not fair, so it's fair sort of empirically. When we look at the samples, we don't see more than an alpha fraction of fairness violations, but we do see significantly more than alpha on the underlying distribution. That's just not going to happen. Okay, that's a very low probability event. Okay, so there exists an M, and we'll say in a minute a number of samples we need, so that the probability that if we draw M examples from the underlying distribution, that H is alpha gamma fair on the xi's, but is not alpha plus epsilon gamma fair on the underlying distribution, this probability is at most delta. So how many samples do I need? Well, okay, for that. Is the statement clear? So what does this mean? If I have my hypothesis H, I can draw a small number of samples, we'll say in a minute exactly how many, and I can verify whether or not this hypothesis is fair. And without relaxing to approximate metric fairness, we couldn't do even that. We couldn't even tell, given a hypothesis, is it fair or unfair? Okay, so this question of auditing is really important. And the minute we relax the definition, it also has to do with generalization, because the question is what I'm seeing on the sample reflective of what's happening with the underlying distribution? And the minute we relax the fairness a little bit, yes, it is reflective enough. Okay, so how many samples do I need, and why is it true?
Log of
Yeah, so the number of samples you need, it's just a Chernoff bound, okay? So it's the probability. People who are not, okay, I'm gonna ask, how many people are familiar with Chernoff, Hofding bounds, probability bounds? Okay, most of you, those of you who are not, it's good reading before tomorrow or during the break. I think the Wikipedia page is good enough. So for every pair of individuals, we have the event on the sample, whether they violate the fairness constraint, yes or no, so binary event, and the probability that the fraction of these events on the sample is not reflective of the fraction on the underlying distribution shrinks exponentially quickly with the number of samples. Okay, so if we want to approximate the probability of having a fairness violation up to epsilon, the number of samples we need is 1 over epsilon squared. And if we want to do it up to confidence delta, we need to draw log 1 over delta over epsilon squared samples. Okay, so that's just a Chernoff, a nice friendly Chernoff bound. Okay, but this is great because not only does it give us auditing, but I claim that now this also gives us generalization that we can use for more powerful machine learning. Okay? So what I want to claim is that not only is the fairness of a particular hypothesis on a training set sort of reflective of how fair it is on the underlying distribution, but in fact, if we draw enough samples, we will have that simultaneously for all hypotheses in a benchmark class that we're considering, simultaneously for all of them, whether or not they are fair on the sample, whether or not they are fair on the distribution is reflected in the sample. That's sort of known as uniform convergence. So even better, and this is what we're going to use in order to do our machine learning. What I want to say is for every, and for now I'm talking about finite hypothesis classes H. And for every epsilon and delta that we might want, if we draw enough samples, and we'll talk in a minute about how many samples we need, the probability that there exists some hypothesis in this class that is fair on the samples, on the examples we drew, but is not fair on the underlying distribution is small. Okay, and the point is that now we have all the hypotheses in H simultaneously inside the probability. Before it was for any one hypothesis, now we're saying for all hypotheses in H simultaneously. Okay, so I'm going to say that it is, hopefully we understand what I mean by that, it is alpha gamma empirically fair on the samples we drew, but is not alpha plus epsilon gamma fair on the underlying distribution, is at most delta. Okay. So why is this true? Or why should we expect, we'll talk in a minute about how many samples we need, but how can we say that it's true for the whole hypothesis class at once? Okay, so it's just a union bound. And again, if these are things that you're not familiar with, Chernoff bound and a union bound, over the break and after the reception today, it's a good chance to refresh. Okay, so the probability that there exists some h is at most the number of h's that we're talking about times the probability that the behavior we don't want happens for each of them. The event we don't want happens for each of them. Okay, so if we use the previous claim, but we just pick our delta, we use it with a smaller delta, which is the delta we want divided by the size of h, then for each of the hypotheses, the probability that the bad thing happens is at most delta over the size of h. There are most size of h such hypotheses, and we get what we wanted, right? So it won't happen for any of them. So how many samples do we need? Someone has to help me, not Cynthia. Okay, so everything we need is already, maybe it's not discernible, but it's already on the board, right? We just need to activate this claim with a smaller delta prime that's written over here. Okay, so just plug in delta prime here, and you'll see that the number of samples you need is log the size of h plus log 1 over the delta that you want, the global delta that you want, divided by epsilon squared. Okay, so just a Chernoff bound and a union bound. And this is great because this allows us to do what's known as the framework of empirical risk minimization, something equivalent to that for learning. Basically, what we'll try to do is we can draw our samples. We can look within the hypotheses in H that are empirically fair on our sample. We can try to find the most accurate one and just output that. And we know automatically, because we restricted ourselves to the class H, we automatically know that our hypothesis is fair on the underlying distribution, so our fairness concerns are handled, and we have similar behavior for accuracy. So the accuracy on the sample is also going to be reflective of the accuracy on the underlying distribution, and we're in great shape for doing machine learning. I want to make a small technical point, which is, kind of a curiosity, but also a call for help. So in the actual technical paper, when we measure fairness on the sample, so if I draw a sample of m examples, I have m choose 2 pairs of individuals. And the event of whether the hypothesis is fair or not on any of these 2 edges between individuals, those are not independent events, right? Because I can have, one person x, and then x1 and x2, and the behavior kind of on the edge between x and x1 is not independent of the behavior on the edge between x and x2, right? Because I just drew one example for x. These are not sort of independent events, and then I drew 2 samples for x1 and x2. If something weird is happening on x, it's going to happen both with x1 and with x2. They're not independent events. So actually, when we measure empirical fairness at the moment, we're doing it using a matching. We take our m examples. We have now m choose 2 edges, and we just pick any m over 2 of those that are a matching, that are sort of disjoint, connecting disjoint edges. And that's how we measure our empirical fairness in order to guarantee generalization. And it would be nice to have a clean, it should be true that you should be able to do this without suffering anything by averaging out on all the edges. That's not what we do, but it should be possible. So that's something for you guys to think about. And if you come up with a nice, clean argument, I'll be delighted. Tell me about it. Yep. Yeah, so we drew m examples. Okay, this is our training set. The point is just that for matchings, the event of is there a violation on this edge? And is there a violation on this edge? These are not independent events over the probability space of drawing examples. because they both have to do with this example x, the first x that we drew. So they are not independent events. So that's the concern. But if I restrict myself and only look at, I pick a matching and I only look at edges that go, say, between x1 and x2, and now this edge between x3 and x4, now the events are independent of, whether there is a fairness violation here and here. So I can use a Chernoff bound the way I know and love. So I just try to do the maximal, I try to get the maximal bang out of my buck from the set of M, and the way I do that is by picking a maximal matching. Okay, so that was a nice...
The technical question that you have, so whether you could, you're doing right like now with...
Yeah, so what I would like to do is to really measure the fraction of violations on all of the M choose 2 edges. And I think I can get away with it by sort of dividing the probability space and just separating it into matchings and then putting them together. But I want kind of like a clean argument, like a direct proof. It's a sort of a pet peeve. I don't know that it's the most important. We'll talk about more important technical questions throughout the course, but I would like a clean argument for why that's fine, to measure the empirical fairness violations by averaging over all the edges and not just a matching. And I don't want to do it by going through matchings. Good. Okay, so great. So, we're all set to do machine learning that's fair using our metric. The one thing I do want to say a word about is this assumption, which might, make some of you cringe, that I needed my hypothesis class to be finite, and that showed up, the size of the hypothesis set class seemed to be really important in the generalization bound, in the number of samples I need. And often we want to use hypothesis classes that are not finite. If I want to do like linear regression or the number of like hyperplanes, I want to use real valued vectors, for example, as my hypothesis class, and the number is not finite. Okay. So we can get around it as we can. So that's a problem for standard machine learning, just if you want to do pack learning and you want your accuracy guarantee to generalize from the sample to the underlying distribution. And also here for the fairness guarantee, for pack learning, you may know kind of the classical measure of complexity of an infinite class. Finite or infinite class is its VC dimension, which I won't define or get into. But the point is that that can be finite. Even if your class is infinite, for example, the class of thresholds over the lines, over the real line, it's an infinite class, but its VC dimension, that's a measure of the information theoretic complexity of the class, and it's finite. And you can simply plug in, instead of log the size of H, you can plug in the VC dimension of the class. That works well for Boolean, for binary classifiers. Here we're talking about classifiers that are sort of real valued because they're outputting distributions. So we need a different measure of the complexity of the class, and the one we use is the Rademacher complexity, which again I won't define, but it's a measure of the complexity of the class. And it would give you a sample complexity bound that for finite classes is no worse than log the size of H. But for infinite classes, and also for finite, it can be finite, and for finite classes, it can be much better than log the size of H. So these are things, I'm not going to cover them, but if you haven't seen them, there's beautiful math and beautiful theory about VC dimension and Rademacher complexity, and I recommend learning about them. The one thing I wanted to say is that once we use the Rademacher complexity, that shows up. So we have here, instead of log of H, we have the Rademacher complexity of H squared, whatever. It's at most log the size of H if H is finite. But the other thing I do want to say that we lose is we have some, we also have some loss in generalization of the gamma parameter. So if your alpha gamma empirically fair, if H is alpha gamma empirically fair on the sample, the guarantee is that it will be kind of alpha plus epsilon of alpha, comma gamma plus epsilon of gamma fair on the underlying distribution. And I guess my alpha and gamma look the same, so we'll struggle with that. Okay, so just to say we can handle infinite classes, Rademacher complexity is a nice measure, I recommend getting to know something about it. I don't remember offhand whether we have to lose something in the gamma. That's a good technical question. I don't remember the answer offhand. Certainly the theorem we prove does lose something also in the gamma. And here we have alpha, epsilon, whatever the loss we have in the epsilon squared, and also the loss in the gamma squared. Okay. Good. So the main thing I want to do, before we go for a break, is now we've sort of come full circle. We have a definition of fairness that can generalize from a sample, and now I want to define the analog of pack learning when we're doing fair learning. Okay, so in a nutshell, I want to write the definition, but we already know in a nutshell what are the two things I want from the hypothesis that my learning algorithm produces. I want it to be approximately fair, using this notion, and I want it to be accurate. And for accuracy, we already know, we have it, what's your name? Sid. Ah, Sid, good. So Sid already hinted to us that for accuracy, we're going to compare with the best fair classifier in our benchmark class H. Good, so this is what we call a pack F learning algorithm. Again, for a class H. So what do we want? First of all, I don't want to assume anything about the metric. So the algorithm should work whatever the distribution is. We don't know what it is, whatever the underlying distribution is, and whatever the distance metric, D, is. And then we have a bunch of parameters. So we want to be able to specify for the learning algorithm the approximate fairness parameters alpha and gamma. And our error parameters, we have the epsilon delta that we know and love, and also our error in terms of how approximately fair we're going to be. So that's epsilon alpha and epsilon gamma. Okay, and now I want to say for any of these parameters, for any choice of parameters, the algorithm, given a sufficient number of samples, should be able to learn a hypothesis that is alpha gamma fair and has competitive accuracy. So there exists a sample complexity M that's finite, and ideally I want it to be, and it will be, polynomial in all the parameters, in the inverse of all the error parameters, and polynomial in the log of 1 over delta. And what I want is that with probability 1 minus delta over the choice of my sample and the algorithm, the learning algorithm's coins, it produces a hypothesis H such that, so we have our two requirements, fairness, so I want that H is alpha gamma fair. And I emphasize this is with respect to the underlying distribution D, which is unknown, and the metric D, which is known to us. Okay, so that's simple enough. You know, if we just look for you know, the best, if we make sure that we output a classifier that is fair on our sample, it will also be almost as fair on the underlying distribution. We just proved that. That's one way of learning. And the second thing that we want is accuracy. Okay, and here, exactly as Sid said, we're going to have our benchmark. So we're going to define the fair subclass, H prime F of H, be the subclass of H that are alpha, gamma, fair. Okay, so that's going to be our benchmark. Now, I just want to say we're not actually going to be able to compete really with the alpha, gamma, fair classifiers because we always have our generalization error. Okay, so I'm going to take a slightly stricter subclass. So alpha, the ones that are almost, a little bit more than alpha fair and a little bit more than gamma fair in terms of the additive error. Okay, just because I need that slack for generalization. I can't, from the sample, I can't distinguish something that is alpha fair from something that is alpha minus less than epsilon alpha. So I need that little bit of slack. And what I want now is that the error of my hypothesis is not much larger than the best fair classifier. Okay, I have at most an epsilon slack. And I think we didn't really prove it, so that's another question for you guys. In a sense, this is the best one could hope for, I claim. Right? If you're going to produce something that's fair, you can't outcompete the unfair classifiers. It's occurring to me now that it's a good question to prove in a formal sense that one can't do better than this. I want to make a note and say that, in fact, for some of our learning algorithms, this turns out to be surprisingly tricky to achieve. Okay, so once we wrote it down and now we know what approximate fairness is, you might think we're sort of golden. But if we actually want to build efficient learning algorithms, the fairness constraints become really tricky. I'm not going to say too much more about that, but I just want to say that for sometimes we'll lower our benchmark. So what we call relaxed. This is actually called in the paper strong PAC-F learning, and for the efficient algorithms that are known, we actually need to relax this. So sometimes we just try to compete with the or we can only show that we compete with classifiers that are, say, something like alpha over 2, gamma over 2 fair. Okay, so that's easier, right? I'm restricting my benchmark class to have even more fairness. That makes my job easier. And this is what the actual learning algorithms that are known today, these sort of fair analogs of things like linear regression, logistic regression, they exist and they achieve these more relaxed notions of accuracy. Good, so I think that's what I wanted to say about the definition of fairness. I already told, yep?
Can you explain a bit more about what's the bottleneck toward achieving proficiency with the first? Like, why take it by two steps?
Yeah, I can try. So the question was, what's the bottleneck for achieving efficiency? So let me say a word about that. I wasn't planning to present. You're being taken on sort of like a highlights tour, or I don't know if highlights. You're being taken on a tour, highlights and lowlights, of what's known in the fairness literature. And I'm not going to get into the nitty-gritty of the efficient polynomial time learning algorithms. But the way they work is using convex optimization, in particular optimization using either convex constraints or linear constraints. So when you're trying to optimize, to actually run an optimization program, say to find the best linear classifier. Okay? So you have the fairness constraints, right? So the fairness constraints are sort of telling you that you can only search within the hypotheses whose fairness error is at most alpha. And depending, for linear regression, you might be able to do it, but when you're trying to do something a little stronger than linear regression, so you're really trying to, say, define a hyperplane, and you want the things above the hyperplane to be classified as 1, and the things below the hyperplane to be classified as 0, you suddenly have a very non-Lipschitz behavior, which happens in machine learning, but now it's showing up for us not just in the objective function that we're trying to maximize, but also in the constraints of the program. and you need to do some polynomial approximation for this behavior, and you need to make it Lipschitzy, and it just ends up hurting all of your parameters that you achieve. So maybe you can ask me that sort of, if you're familiar with these things, hopefully that makes sense, and if you want to know more, you can ask me over the break.
So can you clarify the relaxation again? It sounds like, so if we're going from alpha minus a smidge to alpha over 2, then we're forcing that subset to be more fair. Right?
Yeah.
Because of the fairness violation, so it's a smaller subset. And is that, so then the error of the smaller subset is going to be at least as big, the minimum error of this restricted set is at least as big as the minimum error of the larger one?
You explained it beautifully. You're just missing I just wish you had the mic. So, was there a question?
But so I just wanted to make sure I was understanding it correctly. So the relaxation isn't that you're making that subset larger, it's that you're giving yourself more.
Right, the relaxation is that I'm making my benchmark. Even though I am going to produce something that is alpha gamma fair, I'm not trying to compete with things that are about alpha gamma fair, I'm just trying to compete with the things that have an even stricter fairness requirement. So that's easier for me. It makes my job easier, it makes my accuracy guarantee less robust, less convincing.
But does that defeat the purpose? Because here, in the original setup, you have to compare with algorithms that are a bit less fair, correct? So if you restrict that to things that are more fair...
No, they are also more fair here, right? I'm competing with things that are... What I want to do is to produce something that is fair and is competitive with the most accurate fair thing. That's what we would dream of. Now, because of generalization errors, we can't compete with the exactly most fair thing, because we don't know there's an underlying distribution. So we're already restricting ourselves to competing with something that is a little more fair than ourselves, but just a smidge, and we can control that slack, right? We have this epsilon alpha as a parameter, so we can make it essentially as small as we want by taking more and more samples.
But you're talking about comparing the accuracy.
Yes, I'm comparing the accuracy. So for fairness, we will be alpha gamma fair, period. The question is, who are we competing with in terms of accuracy? Are we competing with the best thing that is alpha gamma fair? That's what I would dream of, but generalization, blah, blah, blah. Can't do it, need to make it a smidge easier for myself. So I would hope to compare with the things that are, almost the entire set of alpha gamma fair classifiers, just like slightly smaller, right? The things that are a little more fair. That's what I would want. And in terms of efficient algorithms, I can't even achieve that. I'm competing with the things that are much more fair. I mean, it's not a trivial, by any means, requirement, but that's what we can get, and I think that's a good open question. So, either coming up with something that is a strongly fair, variant of, say, logistic regression or linear regression, on the one hand, or on the other hand, show that this has to be hard. They show that it really is computationally hard. There has to be some computational price that we're paying. It's an open question. I don't know what the correct answer is. Okay, is there just like a more clever algorithm, a more clever way of doing the optimization, or some totally other different algorithm? Or is there some inherent computational difficulty here? Okay, so it's questions? Great. Oh.
I was wondering if you could mention the source or a good source to read up about the relaxed notion versus the strong notion.
So I think the best source is still the paper, unless there are some lecture notes. So the paper is myself and Gal Yona, 2018, probably approximately Metric Fair Learning, I think is the title.
So what I really, I guess to make my question more specific, what I want to know is if one is to sort of go for the background of the open question you just mentioned, then what is a good starting point is what I want to ask. Do you think this paper is a good starting point?
I think the paper is a pretty good starting point. And if you hate the writing, you can send me hate mail. I think you would also need to know a little bit about convex optimization.
Sorry, but is the reason we consider agnostic learning instead of just normal pack learning because we don't assume that the data is generated by some fair classifier?
Correct.
Okay. Because
Yeah.
that would make any sense like that.
I mean, I'm specifically interested in the case where the data is not fair and is not generated by a fair hypothesis, and I'm using the metric to sort of undo that problem those problems in the data and come up with the most accurate thing that is fair. So I think the realizable setting is even less relevant for this question than machine learning without fairness constraints. Yes, 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 yes.
I was wondering where I can find the result of the form, or a result of the form, fair algorithms won't outcompete unfair algorithms. Is there a formulation of this?
So I think sometimes the question was, are there theorems of the type, fair algorithms will not outcompete unfair algorithms? So sometimes, you can set things up so this is an easy statement. I think it's interesting to ask actually when fair algorithms will outcompete unfair algorithms, because often the benchmarks that we're using are not the right benchmarks, right? If the data are biased, and there is literature on this, Cynthia maybe will help me with a reference, but if the data are biased, so for example, there's some protected group who we have not been admitting to college, and so we don't know about these people with higher potential, if we use a fair classifier, we may just get a better pool of students. But how are we measuring that, right? Like what is the measurement of how well we're doing? We won't be outperforming the unfair algorithm on historical data. Right? We need some other measure of how well we're doing.
Does this learning framework still work with group fairness?
Sorry, could you repeat?
Does this pen learning framework work with group fairness?
Does this framework work with group fairness? So there are lots of works on machine learning with group fairness and constraints like statistical parity or balance for the positive class or negative class. And I'm blanking on references, but you can email me and I'll send you some. However, I'm going to defer to Cynthia's talk in the first half and say that group fairness notions are really brittle, so this is much more robust. Okay, so I don't know, if you're interested in group fairness and you think it's a sufficient fairness guarantee, I would love to have a conversation about why you think, those catalog of evils, the catalog of evils from Cynthia's talk doesn't apply and why that's strong enough in terms of our fairness notion. The good thing about a metric is both that it can convey much more subtle and robust fairness protections. It's also easy to refine it, or it can also be refined so that if we have some improved understanding of what fairness should mean, we can refine the metric, and that's a path towards progress. I think there's a lot to like about that framework. Yep.
An early move in the theory was to focus on probabilistic classifiers instead of deterministic classifiers, so that two people with the very same feature vector, one could ultimately be predicted to recidivate and the other one not, even though the classifier satisfies this individual fairness definition. I wonder why that tracks. Then, if I grade a student exam, two students submit the very same answers, but one passes and one fails, the failed student has cause to complain.
Yeah, so it's an excellent question. The question was about the a priori nature of individual fairness guarantees as opposed to a posteriori. So the definition says that a priori, we are both going to be assigned a distribution, and if we have identical features, we will be assigned identical distributions. And a posteriori, it might be the fact that each of us, with probability a half gets the loan and probability a half doesn't get the loan, and one of us gets it and one of us doesn't. And, that's That's a nature of a priori as opposed to a posteriori guarantees. The big advantage of using an a priori guarantee and using distributions is we can get these kind of really robust closeness guarantees. So there's no getting away from the problem, right? Either we put a set threshold, and people above the threshold get a 1, and people below the threshold get a 0, and then you might be really, really close, but it's sort of like, it's a bummer, one got the loan and one didn't. Or we use a probability distribution to make things more Lipschitz and more smooth. I think that's more fair. It's also more robust to things like post-processing. It has a lot of properties to like. But yeah, I mean, it might in the end be that two very similar, identical people, a posteriori, one of them gets the loan and one doesn't. Okay, good. So we'll take a break and we'll come back, let's say at 3:35, 5 minutes late.